Welcome back to ECE 501B. Homework number 5 is due on Thursday, and homework 6 is due in a week, and we have our second exam a week from Wednesday. I will not be in office hours this Friday. That's homecoming, and I'm occupied with other activities because of homecoming, meeting with different people. But you should be able to find practice material for exam number 2 on D2L to get you prepared for the exam. The other thing, people were asking about the project and due dates, and now I have 3 different deadlines for the project. The second and third are really when the project is due. The first deadline for the project is just an okay between me and you that what you've suggested for a project seems to be acceptable. And that may simply be you cutting and pasting the email that you sent to me or the email traffic, but somehow I want you to maybe formally document deadline number 1, which is the 7th of November, just so that we're all on this right page. And then the last day of class is when your project is due, and that's deadline 2 and deadline 3. Deadline 3 is really a reflective paragraph of your project. What did you learn? How did you do with respect to the project relative to the class material, etc.? But deadline 2 is really the main project report. To get you ready for that project, in the course resources unit, which is near the top of the page, is the second textbook, Signal Theory. That gets into the infinite dimensional case of functional analysis. But then there's the $25 billion eigenvector. Obviously, that's dealing with eigenvectors. But you could read that paper, not that you wanted to do your project on that paper, but that would give you an idea as to what you could possibly do if you were looking at a different topic, as far as how do you ask questions as you're going through another resource that you might be interested in. The football ranking is dealing with positive matrices, and we'll get to positive matrices hopefully shortly. Principal component analysis works with symmetric matrices and also positive matrices, and the road to reality by Penrose. I have relation that are Penrod, so I may be saying that wrong occasionally, but it's Penrose. We have a more Penrose inverse to a matrix, and that's the person that's tied to that. And the road to reality is the first 4 chapters, or chapters 2, 3, and 4 of his Road to Reality text, which goes into really sort of this way of thinking mathematically relative to relating it to reality. And so that's just maybe a nice read, but maybe that will inspire something for you to work on for a project. Today what I want to do is probably finish chapter 6. We'll recap orthogonal projection. We'll get into vector space direct sum decomposition, the projection operator, minimization problems. Now we're getting into some fun applications of linear algebra, and the minimization problem is a big one. We'll go back and pick up again or reintroduce linear functionals, and chapter 7 begins with adjoints, and now we get another symbol to use, which is the dagger. I just like to say T-dagger, but that's now the adjoint operator that we will be introducing to start chapter 7. And that's really just a way to slide a linear map to the different slot in an inner product. So if we had TV in the first slot, and if we wanted to move that linear map to the second slot and free up or just retain a vector V in the first slot, we would then slide that over, and it would then be a T-dagger, or the adjoint, in the second slot. But we'll get to that maybe at the end of class. Relative to orthogonal projection, if we have a subset U in our vector space V, then we can define the perpendicular component, or the perpendicular subspace to that subset, called it U perp, and that's all the vectors in our vector space V that are orthogonal to any of the vectors U in that subspace. And even if the subset U, or if U is a subset, that still allows U perp to be a subspace. Its orthogonal complement is a subspace, even if U starts out as a subset. And we can show that U perp is indeed a subspace because it's closed under linear combinations and it contains the zero element. And those are the properties we need for something to be a subspace. If it's a subset of a vector space, it already incorporates a lot of that built-in machinery or properties from the vector space, and we simply need these really three properties: addition and scalar multiplication and the zero element, for something to be a subspace. We also talked or introduced Theorem 47, which is if U is indeed a subspace, more than just a subset, then we can build or decompose our original vector space V into these two orthogonal components, and we now have this direct sum decomposition of our underlying vector space in terms of a subspace U and its orthogonal complement, or U perp. And now we will pick up with the following. If U is a subspace, then the direct sum representation of the overall vector space V implies there is a unique decomposition of all vectors in V in terms of elements in these orthogonal subspaces. That's what we get with a direct sum decomposition, is this unique representation, which really says that for all vectors little v in our vector space capital V, we can break that vector V up into two pieces. V can be written as the sum of U plus W, where U is now in this subspace big U, and W is coming to us from U perp. And that's a unique decomposition because we are dealing with a direct sum decomposition of that vector space, meaning we can get part of V in U and the other part in the orthogonal complement of U, which is U perp. And the nice thing about this is we can now use that property to do projections. We can now project orthogonal to an underlying subspace. We use this feature to define a projection operator and we will denote that projection operator as capital P sub capital U. And this is actually then an orthogonal projection of any vector in the underlying vector space capital V onto the subspace U. Or if we write that a different way, or just restate it, for all vectors little v in our vector space capital V, we just showed that we can do this decomposition of V because we have a direct sum decomposition of our underlying vector space capital V. We can construct V into two pieces, a U piece and a W piece, two different vectors where U is in U and W is in U perp. And if we split V into these two pieces, we can actually define this orthogonal projection P sub U of V as giving us the U that we're after. So if we can find this orthogonal projection, or this projection operator P sub U, then we can project any vector in our vector space into this underlying, or this subspace, little capital U that might have elements little u. Relative to this projection operator, it enjoys certain properties. One is this projection operator is a linear operator. The range of that projection operator is actually all of the subspace U. The vectors that are orthogonal or in the null space of that projection operator actually equals U perp. And if we look at the component that is orthogonal to the subspace U, which is now this W that we've been calling, then that W belongs to U perp. And that's the piece of the original vector V that's orthogonal to this subspace capital U. And we have been calling that W. The other property of this projection operator, or another property, is that if we applied that projection operator again on some vector, we really haven't done anything. We're back to just the projection operator. And one more property is if we look at the norm of the result of taking a vector V and projecting it onto this subspace U and look at its norm, then that norm is going to be less than the norm of V. And again, you can just think in two dimensions, where if you just had this vector V in the xy plane and maybe you projected that V onto the x-axis, hopefully it's clear that the length of that projected result on the x-axis is less than or equal to the overall length, which is now, you can think of like a hypotenuse of a right triangle. And that's what that last statement is really saying. But in a more general case, because we're dealing with maybe higher dimensions than 2. But that's the picture or the intuition that you can maybe think about when you're seeing that last property. We can also use something that we've already used. We can use our result from earlier to actually create this projection operator. Suppose that we now have a list of orthonormal vectors, let's say m of those, and they are actually a basis for our subspace U. Here we're saying then our subspace U is m-dimensional. If E1 through E sub m is an orthonormal, basis on U. And if it's a basis, what does that mean? It spans, and those vectors are linearly independent. And in this case, they're orthonormal, which means that if you take the inner product, pairwise inner product with any of those, you get 0, and they have a length of 1, or a norm of 1. But if we have that basis, then if somebody's interested in projecting a vector V onto the subspace U, we can actually do that by this inner product scaling these orthonormal vectors, the sums of those, where we now take V inner product with E1, or what's the component of the vector V along this orthonormal vector E1, and that will then scale or weight that direction, E1, plus the vector V in the direction of E sub 2, or that component of V in E sub 2, scales E sub 2, and we just keep going, and eventually then get down to V inner product with E sub M, and that component of V along E sub M scales the E sub M vector. That you should find in the textbook as equation 39 in chapter 6. And that's now a pretty clean way to do these projections. It's just a collection of inner products with your orthonormal vectors, and then using those inner products to scale or weight those orthonormal vectors. We can now use that to perform minimization problems. If we now have this ability to project onto a subspace, you give me a vector V, I can now find a vector U in the subspace U that's close to that vector V, or closest to that vector V. Which puts us in this domain of minimization problems, where we often run into problems that can be cast in the following form. Meaning we may be given a subspace U, and we are given an arbitrary vector in our underlying vector space, or the overall vector space, capital V. That may be given to us. We know U is a subspace of the vector space V, and somebody gives us a generic vector V in the overall vector space, capital V. And we are then asked to find a vector U, little u, in the subspace capital U, such that the norm between V and U is minimized. Or find U that is closest to V when U stays in or lives in the subspace capital U. And to do that minimization problem really just requires us to utilize the orthogonal projection that we've just defined. The orthogonal projection gives us just the tool do the above minimization problem. And one way of expressing that is written in the following proposition, which is proposition 56, which is titled Minimizing the Distance to a Subspace. Here, suppose we have a subspace U. If U is a subspace of our underlying vector space V, and we have a arbitrary vector little v in our vector space capital V, then the norm of V minus P sub U of V is less than or equal to the norm of V minus U for all U belonging to our subspace capital U. And if we have equality in this inequality, then this projection of V onto U is actually U. We have equality when that's true. So let's see if we can sort of convince ourselves of this relationship between you give a subspace U and somebody gives you a vector V. And you say, okay, project that vector V onto the subspace U. Then if you just went into the subspace U and started walking around, figuratively, and you picked a vector U and then calculated the distance between V and U, or V minus U, then that distance is going to be bigger than if you orthogonally projected that vector V down onto that subspace U. And here's how we can show that via a proof. Suppose that we're given a U that's an element of this subspace capital U. Now let's look at the norm squared of V minus the projection of V onto the subspace U. And we can now write that as what we started with, which is the norm of V minus P sub U V squared. So we could say that's equal to that, but we're going to now on the right include an additional factor, which is non-negative, which is P sub U, or the projection of V onto U minus U. Meaning that inequality should be believable. We had an equality and then we just add a piece to it. But look at what happens, or what's going on inside these norms. Where does this vector live? Or maybe we should start by looking at where this vector lives. Where does the result of projecting a vector V onto the subspace U live? On the right-hand side, in the first, or in the far right norm squared, P sub U of V lives where? That's in U, and we're subtracting U, so that must live, it's a linear combination in U, and U is a subspace, so that vector is in U, capital U. What about the other vector? Now we have V, and we're subtracting a vector that's in U. Or this is now, if we looked at this, this would actually be then in the orthogonal complement to U. This is the orthogonal complement of we're now projecting V onto U, and we're taking that piece away from V. So this is now in U perp. And we could think of this as, now let's just call this a vector A, and that a vector B. But we now have A and B in two orthogonal, or A and B are orthogonal. They're in two orthogonal subspaces. What can we do if we have A squared plus B squared, and A and B are orthogonal? Then we have C squared, right? That's equal to C squared, or that's the Pythagorean theorem. So we could now say that what's now on the right is equal to A plus B, which is C squared. But what is A? A is just V minus P sub U V, that's A, plus B, which is P sub U V minus U, that's B, and I'm now saying that that is some combination of A and B. That was supposed to be a plus sign, but it got a little bit out of hand. What I'm doing here, though, is actually applying yes, so I forgot my square here, so there's C squared. So this is now the Pythagorean theorem that I'm using to produce the right-hand side relative to the left-hand side, V minus P sub U V. But what magic now is happening inside that norm bars on the right, my most recent right-hand side? I now have P sub U of V minus P sub U of V. Those are canceling, and I now have V minus U. So that I can now say that the left-hand side is less than or equal to V minus U squared. And that's really what we were setting out to show. That if we take the square root, we have the norm of V minus P sub U of V, the projection of V onto U, and subtract that from V, that's going to be less than or equal to V minus any U in our subspace capital U. Or the geometric interpretation, as I tried to describe earlier, let me sketch it now, can be visualized. Suppose that this is now our subspace U, and somebody now gives us a vector V that's not lying in that subspace. Here my subspace is one-dimensional. But what I want to do now is take the component of V that lives in U and minimize the distance from V to U, so that this is now living in U perp, and this vector, or this point, is the projection of V onto U. And if you move that point on U around, do you see that the component that's in U perp is not orthogonal, and it's actually longer? So this piece right here is V minus U. And we're actually finding a particular u that makes this distance or length between V and the subspace U as short as possible. If you slid this point around, if you went over here, then this length is longer than the length that I've shown in red dashed. Or if you went over here, those lengths are all longer than the red dashed line. Meaning this particular point right there is the closest point in the subspace U to the vector V. And that's what we're wanting to find or obtain via this orthogonal projection. We're trying to now create or find this little u that's as close to V as possible while we're staying in the subspace U. And this now is what we're doing when we have minimization problems. We're trying to find the vector u, little u, in the subspace U that gets us closest to V that we possibly can. And if we do this orthogonal projection, where this dashed line is in U perp, then we've achieved that minimization that we're after. So the solution of the general minimization problem is to actually take U to be equal to the orthogonal projection of V onto U. And U, remember, was a subspace in our underlying vector space V. And we know how to do this minimization from before. We can simply do this decomposition relative to the orthonormal basis on our subspace U. But earlier we saw if we had an orthonormal basis on our subspace U, for example, E1, E2, up to E sub m, then using equation 39 in chapter 6, the orthogonal projection of V onto U is just this linear combination of these orthonormal vectors scaled by the component of those orthonormal vectors in the direction of V. So this is V inner product with E1, scaling E1, plus V inner product with E2, scaling E2, etc., down to V inner product with E sub m, scaling E sub m. Which means that we need to, if we want to do this minimization problem, we simply have to create or build this equation. And how are we going to build that? What is required for us to build this equation given a vector little v and a subspace U? What's our first strategy, or what's our first step in that process? If we want to create this equation, and somebody gives you a subspace U, which is a subspace on the vector space V, and then they give you a vector little v in capital V, and they say, oh, just do this, what do you have to do? So the first step is to find an orthonormal basis of the subspace U. And how could you do that? You could just find, well, you tell me. How do you find an orthonormal basis for a subspace? If I gave you the xy plane and I said, give me an orthonormal basis, you could immediately find an orthonormal basis for the xy plane. What would you do? You would just give me those unit vectors, one in the x direction and one in the y direction, right? Or somebody might say, oh, I'm just going to draw two lines in the xy plane, and you can create your orthonormal basis from that. What would you do? Well, you could say, oh, give me your first vector. You could normalize it, do the Graham-Schmidt process. Then, from that, take away the component of your second vector in that first vector's direction, and that's now your second vector in that orthonormal basis of the xy plane, although you would obviously have to normalize that result. But then once you have that, now you have your e's, now you simply form the inner product of the vector v with those orthonormal basis vectors. Question? So the question is, maybe we're confusing things a little bit, maybe it was my explanation, but V and capital U are not necessarily related. They're just both living in the underlying vector space capital V. So now you have this underlying vector space capital V, but somebody's given you a subspace and they say all we can do is live in this subspace, and you now need to project little v onto this subspace that we can live in. So that now what you have to do is you have to start with the subspace that you're living in and create an orthonormal basis from that, independent of v, little v. So now that you've created this orthonormal basis of e's, e1, e2, e sub m, now is when you go and say, okay, what was your v again, little v? Then you simply take the piece of v in the direction of E1. E1 was not built based on v. Does that help with trying to understand this expression? So that's our strategy, actually, is we simply do sort of this two-step process to do a minimization problem. The solution comes down to finding orthonormal basis. Those are the e's, and those are found on our subspace capital U. And once we have the e's, then we just go to town. We just start doing these inner products. We find the component of little v in the direction of each of these e's and use those components to weight those orthonormal vectors and then form that linear combination. Solution comes down to finding orthonormal basis on the subspace U and then computing inner products. Which is really just the above equation. And if you want to see an example of this in action, you can go to page 199 in your textbook and look at what Axler has in terms of fitting a polynomial to sine of x. Axler has a good example involving finding a polynomial approximation to the sine of x. And you know from maybe calculus or now just a Fourier series expansion of sine of x. And if you look at that example, you'll see that this polynomial approximation does a much better job of curve fitting this sine x over this limited region between, let's say, -1 and 1 than the traditional, maybe calculus-based Fourier series approach. So you might look at that, although that's taking place in function space, not necessarily in this finite dimensional setting, the idea is still very clear. You have this subspace, which is now maybe a fifth order polynomial in this infinite dimensional space, and now you want to curve or find the projection of sine x in this fifth order polynomial space, and what kind of an approximation can you build? Actually takes place in a function space, but now you have the understanding based on this decomposition of a vector v into this directions of your or the orthonormal basis describing a subspace capital U. So now what you're doing is you're trying to approximate this sine of x, which is infinite dimensional, this function, on a 5-dimensional or a polynomial space that's maybe a fifth order. So if it was x to the 5, then you have this 6-dimensional space because you have now a constant. And it's pretty interesting to see how you can hardly see that the two curves of this approximation and the actual function differ until you zoom in to maybe 300 times magnification, and then you can start to see some slight variation between the two curves. Whereas the other approximation that you're more familiar with, it's pretty obvious with no magnification that they are not equal near the tails of that approximation. Let's now return to something that we, I believe, have already talked about, but let's revisit that now that we have, again, this inner product and we want to be using the power of that, and that's this concept of linear functionals, where a linear functional on a vector space V is a linear map between the vector space V and the scalars. We usually were saying F, and the scalars, where F could be real or complex. That's the linear functional. We are simply going from our vector space and mapping to the scalars with a linear map. if we actually pick a vector, let's say W, in our underlying vector space V, then we can create a linear functional through this inner product. Then the inner product with V and W is a linear functional on our vector space V. Remember that W is now fixed. If we pick a W and fix it, now you can show that for any vector V on our vector space V, this inner product is a linear functional. It's going to map any vector little v into a scalar. And it will do it linearly. So we know that this inner product is a linear map, and it takes us to the scalars, and now we're calling that a linear functional, or we can call it a linear functional. What's maybe more interesting, maybe we could go so far as to saying what's surprising is that for any linear functional, we'll now call it phi, on our underlying vector space capital V, we can pick a vector W in capital V such that if we applied this linear functional to a generic vector little v, we can find a vector W that could do the same mapping through this inner product, where now we take the inner product of V with W. Meaning if you are given any linear functional phi that now will map a little vector V on our vector space capital V into the scalars, then no matter what that looks like, we can actually find a W, a vector in our vector space V, such that the inner product of that W with any vector little v in our vector space V performs the same linear functional that phi sub V would have. And that's now available to us as a theorem, that property. And this is actually called the Rees representation theorem. Where now, if we're given this linear functional phi, then there is a unique vector, let's say little u, in our vector space V, such that no matter what vector little v we put through this linear functional, phi, we can make that be the same as this inner product of V with this unique vector little u. And that's true for all vectors little v in our subspace capital V. So let's show that with a proof. Suppose now that we have an orthonormal basis on our vector space. you're now seeing that we play a lot with orthonormal basis vectors, so the Gram-Schmidt is very important. You give me a collection of linearly independent vectors, we can Gram-Schmidt those and get this orthonormal basis for our vector space capital V. So let's assume that we have one, and we're going to call it E1 through E sub n. This is an orthonormal basis on our vector space V. Then we can perform the following steps. Suppose that we now had this linear functional applied to a generic vector little v. And we may shorten that notationally to just be phi sub u. I'm sorry, phi sub u, v, phi sub v. Now what we want to do is take that phi and operate on v, but now let's rewrite v in terms of this set of orthonormal basis vectors. And we can do that. We can do this orthogonal decomposition of v. How do we do that? Well, we take the piece of v in the direction of E1, and that now scales E1. We take the component of v in the direction of E sub 2 and scale E sub 2, and we just keep going. I'm going to run out of room. I'm going to have to widen my paper. So that now we have v in the direction of E sub n, and use that to scale E sub n. This, inside the bracket of phi, is our vector v, and that's the orthonormal decomposition of v in terms of this orthonormal basis E1 through E sub n. Now, the next observation to make is, what are these inner products in terms of that piece, this piece? What kind of a object are they? Those are scalars, aren't they, that are weighting these orthonormal bases. So these are all scalars. But if those are inside the argument of a linear functional, what can we do if we know that phi is a linear functional? How can we now maybe move those scalars around? If this was phi of alpha 1 E1 plus alpha 2 E2, etc., now we can just slide those scalars outside the phi. So that now we can, by the linearity of the functional, we can now re-express that as this scalar VE1, where phi is now applied to the vector that was being weighted, which was E1, and we had this shorthand notation. We were saying that was E sub 1, plus VE sub 2, and that's now going to scale the linear functional applied to the second orthonormal basis, E sub 2. And we just keep doing that. And we were able to do that because we realized that these inner products, the result of that inner product just produces a scalar. And we are starting with a linear function, or a linear functional. So that this now is, at the end, the inner product of v with E sub n, and that now weights this linear functional applied to the nth orthonormal basis vector. But what are these linear functional results? What's the linear functional doing? If it's a functional, it's taking some vector, and where is it mapping it? If I had a linear functional and I applied it to a vector, what would the result be as far as a type? It's also going to be a scalar. So now all of these phi sub e sub j's are scalars. And what do we know about scalars and inner products? Can we push that scalar into a slot in the inner product? Of course. And let's now put it into the second slot. And if we put it into the second slot, how does it need to go into the second slot? It's now this conjugate homogeneity of the second slot, meaning our next equation is going to be utilizing the conjugate homogeneity of the second slot, which now says that, oh, I'm going to have the inner product of V with this scalar phi sub E1's conjugate, complex conjugate, times the vector E1. I'm just sliding this scalar phi sub E sub 1 into the second slot of that inner product. And I can continue to do that, second slot sliding, with these other linear functionals. Those are just scalars. So that I now have V with this phi sub E sub 2 conjugate E sub 2. But now I just have this combination of inner products, and I have the exact same vector in the very first slot, which maybe is indicating maybe I can abbreviate this or compact this into just one inner product by applying another property of the inner products. The second slot enjoys additivity. And I can now use that additivity property to make all n of these inner products just one inner product. So the next equality is going to take advantage of the additivity of the second slot, which now says that V is going to be inner product with phi sub E1 conjugate E1 plus phi sub E sub 2 conjugate E sub 2, etc., plus phi sub E sub n conjugate E sub n. But all of that now in curly braces is just a vector. It's now a weighted vector of these orthonormal basis vectors. And I could now say that that is my U. Which really completes my construction activity. So we can take off our hard hats. What do we have? So we have phi sub V is now actually equal to the inner product of V with U. And if somebody says, well, what's this vector U? U is belonging to our underlying vector space, capital V, and we now know how to build it. It's just going to be exactly what we derived. U is now going to equal this linear functional that we started with applied to the first basis vector. That will give us a scalar, and we will complex conjugate that scalar, and we'll use that to weight the first orthonormal basis, e sub 1, plus that linear functional applied to the second basis vector, e sub 2. Conjugate that and use that to scale e sub 2, and we just keep going, where we now have the linear functional applied to the nth basis vector. We complex conjugate that, and that's now going to scale our last orthonormal basis vector, e sub n. We now have created a vector u, or we now know that a u exists. I think in our statement we said it was unique. Is it? Is it unique? Well, let's just assume otherwise. Let's assume that we can find two little u's that give us the same result when we apply this linear functional to a generic vector little v. Meaning, suppose that we can now find an u1 whose inner product with v gives us that linear functional's value when we apply it to v, and we can also find a u sub 2 that does the same thing, and that's true for all little v. But if we have this equality on the right, then we can use that to essentially push one to one side or the other. Subtract from both sides maybe the inner product of v with u sub 2. So that now we have 0 is equal to v inner product with u1 minus v inner product with u sub 2. And that's true for all v. And now we can utilize these properties of inner products, or the additivity of the second slot. First slot vector is the same, and we can now write this as one inner product of v inner product with u1 minus u sub 2. And that's true for all v. Here's maybe the hard part of this proof of uniqueness of the u's. This is true for all v. If it's true for all little v, let's pick a particular v. And the particular v that we're going to pick is actually the v that's in the second slot, u1 minus u sub 2. If this is true for all v, then it has to be true for a particular v. Therefore, consider a particular v, and let's make that particular v, in fact, be u sub 1 minus u sub 2. If that's the case, then now we know that the inner product of u1 minus u sub 2 with the vector u1 minus u sub 2 is 0. But now what do we know one of the properties of the inner product is? So now this is the definiteness property of that. The only way that this inner product could equal 0 is if both slots are the 0 vector. Since it's the same vector, then that vector is equal to the 0 vector. But the definiteness property of the inner product says that if I have A inner product with A equaling 0, that's true if and only if A is 0. That's the property that we're using, which applied to our particular case, therefore, u1 minus u sub 2 must be the 0 vector, because u1 minus u sub 2 was the vector in that slot, or the first slot and the second slot. And now I can just push one of those to the other side, and I can now say, oh, even though we started with u1 and u2, now we've just shown that they're the same, which says then, therefore, u is unique. Not only does it exist, but it's unique, and that now allows us to complete that proof. And that actually brings us to the end of Chapter 6, or what we will talk about here. Let's now go into Chapter 7, where Chapter 6 was maybe these inner product spaces, which was dealing with generic vector spaces that contained an inner product. Now let's look at putting operators on those particular spaces. Operators on inner product spaces. We just continue to put more and more structure and information into these pieces. We now have inner product spaces. Now let's look at what happens when we have operators on those, or maps on those inner product spaces. First, let's just talk about a map in general, and one such variation on a linear map, which is what we will call the adjoint. And that's also a linear map. But for this adjoint, we actually need two different inner product spaces, because we're going to have two different inner products, and we're going to set those equal to each other. And one inner product needs to be defined on one inner product space, and another inner product needs to be defined on another, but we can set them equal because they're both giving us scalars. But the vectors that they start with may be coming from different inner product spaces. Okay, so now maybe we need to put our helmets back on. Go ahead, I will wait. I want us to be safe. But now let's look at what we have. If we have a linear map, T, and again, in the most general sense, we are mapping from some input vector space to some output vector space W, that's what we're starting with. Where here, we are going to need an inner product space for vectors in the capital V, and we also need an inner product space for vectors W in capital W, where this is now our input vector space, which we will then make even more specific to an inner product space, and this is our output vector space. We haven't yet advanced to our next textbook. V and W are still finite dimensional. So V and W, or capital V and capital W, are both finite dimensional inner product spaces over the same set of scalars F. That's maybe the distinction. Those scalars need to be either real or complex. We can't be mixing complex with reals. So now if we have T, a linear map, then, and I just really enjoy this part, T dagger, that's now supposed to be, I did it too hurriedly, I was so excited, but that's now a dagger. And just to make it confusing, Axler uses what I've been using for conjugate to be his dagger. So Axler uses this star for his dagger. But this T dagger, which is now the adjoint operator or map, is a map from W to V. So now we're going back. We're going from the what was the output vector space into the what used to be the input vector space. We're going to define it by picking a W in W and given a phi on our vector space V such that this linear functional applied to V is equal to the inner product of TV with W. We know that that is true, or we can find a W. But where are those vectors inside this inner product? Where do they live? Well, V, through this linear operator T, goes into the output vector space, capital W, and W was starting in capital W. These are now vectors in W. But we're now trying to define this T dagger, which when that linear map is applied to W, that is the vector in our original input vector space such that phi sub V, that was the original linear functional applied to V, is now going to equal the linear or the inner product of little v with T dagger W. But where are these vectors? Where do these vectors live? If you just look at the isolated vector and where it belongs, then you realize that, oh, T dagger was mapping from W into capital V. Those are both vectors in the original input vector space, capital V. But what is phi of V? Well, that's the same scalar, and now we've just said that those both have to equal these two inner products. Meaning, the linear map T and its adjoint, T dagger, are actually defined such that we have this equality between the following two inner products. T, V, inner product with W, is now equal to the inner product of V with T dagger W. What in the world is going on? Well, just don't get too confused, but what have we actually done? Now we've moved a linear map from slot 1 to slot 2. Just think of it in that simplistic way. We had a linear map, capital T, that operated on V. Now maybe we wanted to just have a vector in that first slot, and we wanted to move that linear map into the second slot. Well, it's not always going to be just the linear map in the second slot. It's actually the adjoint of the original linear map. So changing the slot of the linear map is really what the adjoint is allowing us to do. And we've now actually, now that we've made this result, we're going to have to stop, but I hope that you now go home and you're so excited about this adjoint. But what that's now allowing us to do is slide this linear map between the first slot and the second slot. But it's not necessarily always going to be the same linear map. In some cases it may be. It may be self-adjoint. All fun things that we get to now start talking about when we get a little bit further in this concept of operators on inner product spaces.